We're very pleased that Remi Rhodes made it through the Eurostar fires yesterday, and he's able to start his lecture on Gaussian multiplicative chaos.
Thank you for being here. I would like to thank I would like to thank also the organizer for inviting me. So so I'm going to give a short lecture about Gaussian multiplicative chaos. So before I start, I would like to say that I'm not exactly what I call fluent in English, so you have to be patient with me. And so if you have questions, I don't mind being asked, just speak slowly and it will be okay. So, well, a short introduction. So, well, I'm going to review a theory called the Gaussian multiplicative chaos. Well, and it is rather fair to say that this theory is born maybe in 72, following an idea of Mandelbrot, and it was this theory was suggested in the context of turbulence. I'm not going to discuss turbulence this week, but well, Mandelbrot suggested that some measure I'm going to discuss would be well fitted to stick to fit turbulence, and this theory was made rigorous in 85 by Kahn, and ever since there has been a lot of application in this theory. Maybe I could quote a few field of applications. So we have, so as I said, this theory is born in turbulence, following Mandelbrot, then Kahn. Well, Kahn was more, it was more about mass, but then we could quote also Frisch. I'm not sure of the spelling, but it is Uriel Frisch. Okay. And then there has been some works in mathematical finance. Also by Mandelbrot. And then some extension of this theory were studied by Bakri, Delour, and Musi, and many others, but they were the first mathematical finance, sorry. Then there have been some application in signal analysis. There have been also Mandelbrot, always him, and Barral. In well, what is called UV quantum gravity. This is the point I'm going to discuss regarding application. So the first, there's been a lot of works by physicists. We should surely quote Polyakov, David, Dissler, Kawai, who introduced some exponential of a field that Jason talked about this week. This is the Gaussian free field. So you have David, Dissler, Kawai, and in mass you have some work by so Duplantier, Jason, and myself, Scott Sheffield, and Vargas, and many other ever since, not like Nathanael and Christophe Garban and a few other works. And finally, I would like to quote a very recent work with relation with endometric theory by Christian Webb. Matrix theory. This is about the convergence of the determinantal polynomial of random matrix. So this is Christian Webb. So this is a list of applications. You can find them, many of them on arXiv. If you want, what I want to discuss in my application, this will be this point. And so basically, the plan of my lecture will be the following. First, I will review Kahn's theory. Kahn theory. So basically, the purpose of this theory is to define some random measure, which can be written like this. So here you have a random measure. Okay, so the measure sigma is a random measure, a deterministic random measure. So in most applications, you take sigma equal to the Lebesgue measure. Okay, and here you have an exponential, and this field here, x, is a Gaussian field. So if it were a fairly defined function, there is no harm in defining this exponential here. Okay. The point is that the x we want to consider is not a function. It will be a random distribution in the sense of Schwartz, so that it's not clear how to take the exponential of a distribution, right? So depending on the structure of the field, we will see that we can give sense to this exponential. Okay. So then I will review Kahn's theory and give you references for the main results. Then I will insist on applications, well, treating the more important examples, especially the Gaussian free field. So GFF and translationally invariant log correlated fields. So translationally invariant log correlated field. Then I will discuss some further properties that are well known ever since. And then, so this is the first part will be just about explaining Kahn's theory. Then I will give you a general framework for convergence in law. Then a general framework for convergence in probability. And finally, I will explain the relation between this measure, between so Gaussian multiplicative chaos and random planar maps. So random planar maps is basically the content of the lecture by Grégory Mirmont. So at the end of my talk, I will explain how to connect. What are the conjectures between this measure and random planar maps? So, well, this is my my plan of my lecture. So before we begin, I give you a few so the first part is about well, this is the chapter 1. So this is about reviewing Kahan theory, and the first thing I want to tell you is a very important lemma proved by Kahan. Let's call it the comparison principle. This is the main, well, this is the cornerstone of his theory, and I want just to state this elementary lemma, which is the following. Take two Gaussian, take two Gaussian random vectors. Call them AI and BI, centered, so two Gaussian random vectors. Which are centered. And the key thing is that you can compare their covariance. Okay, so we assume that for all I, we have the following relation: AI, AJ, say less than the covariance of BI, BJ. Okay, so if you have this inequality, then you can compare. Then for f, you take a convex function, convex. You can compare the exponential of this random vector. So you take the exponential, the expectation of f So the object I introduce here is this is some kind of discretized version of the exponential of Gaussian fields I want to construct. And so at the discrete level, if you can compare the covariance, you have this relation between this discretized random measure. So in some way, the measure we want to construct will be increasing with respect to covariance seen through convex functions. Okay, this is the main lemma of Kahan's theory. It has been used in other contexts as well. For instance, for the Sherrington-Kirkpatrick model, but well, I will just focus on this Gaussian multiplicative chaos thing. So I don't prove it, it's rather elementary. You can find a proof of this lemma in Kahan's paper. So maybe I can give you a reference. Well, it just uses the integration by parts lemma for random vectors. So ref, so Jean-Pierre Kahn. Well, this is a French paper, so you will be happy to read it. Well, actually, if you don't understand French, you just have to read the math part, and this should be fine. So this is in Annales de la Faculté des Sciences du Québec. Yes, but if you send me an email, I can send you the paper. I have a scanned version because you cannot find it on the web. I am not responsible for this. Okay, so. But what you see, the proof is clear. So, so Kahn's method now. So recall that you want to define some random measure. You have your exponential of x, sigma dx. And here you have a random distribution. So in a way, this is a very badly behaved function. So when you have a bad function, the first idea you may have when you want to deal with it is to regularize it. Okay. So, for instance, you may want to consider a convolution. This may be the more natural way to handle the problem. You take x, you make a convolution with some smooth function with a modifying sequence, call it rho epsilon, and you want to plug this, call it x epsilon. Okay, you want to plug this expression inside this relation, okay, and take the limit as epsilon goes to 0. Okay, this is the first natural way to handle the situation. Well, and this is not a Kahn strategy. Okay, well, I will have a word about this strategy in my part 3. Okay, this is the section for convergence in probability for general cutoff. Here I will explain Razor Kahn's method. It's not very intuitive, but it's very elegant, and actually based on Kahn's method, you can recover all the other situations, especially this one. Okay, so I rather begin with Kahn's method. So. So Kahn's idea is to deal with to make the framework is to make the framework well fitted for using martingale's techniques. So basically, his method relies on the notion of kernels of sigma positive types. I'm going to explain what it means. So, so first, first the idea. Okay, so you have your random distribution. So it acts on, say, a smooth function. Okay, and you can define the covariance kernel. So we'll assume that X is centered. meaning that this kernel, so this random distribution will act on a smooth function. So this means that for each test function, you will have something like this. Is equal to 0. And you can define its covariance kernel if you take two smooth functions. So this will be a double integral over the space you live on. Say phi of x k. You will have a kernel k. So for test function, you can define a covariance kernel. Okay, and this kernel, we will assume that we can write k as a, which is of sigma positive type. So what does it mean? We want to find decomposition of k into a sum. Recall that this is a bad kernel. Okay, in some sense, it will have a singularity or something like this. And the idea is that you can write this kernel as a sum of nice kernels. Okay, and we will use an infinite sum of nice kernels. So we will take as an approximation for k the partial sum of this series. Okay. So well, the idea is that k is a sum, a series of nice kernels. Maybe I don't remember the order I write, so maybe I should write on this one. It's random. If you don't want that I erase, just say stop. So the definition is the following. Well, so you take locally compact metric space. Metric space, say, so G is my space, and say rho is the metric. While G it's better for the metric. Okay. And well, a function k, so defined on the product g times d, taking values in say R plus the closure, well, and eventually plus infinity. So instead of sigma positive type, if it can be written as a sum, well, where the kernels Kn are nice. So it's a good definition. So what do I mean by nice? I mean they are where Kn, the Kn are continuous. Positive definite. and positive. Okay, recall that positive definite just means that you are the covariance kernel of some nice random function. Okay. Well, so and more precisely, you assume that there is a sequence of continuous Gaussian processes I call them xn, so they are defined on G and they are independent. Okay, so this is a sequence of independent random functions on G. And such that Kn is equal to the covariance of Xn. So, well, all the fields I will consider in my lecture are centered. Okay, so I don't write it again. Everything is centered here. So, so you assume that you have your kernel, which can be written as an infinite sum, and each term in the sum is a covariance kernel of some nice, I mean smooth Gaussian process. Okay, smooth with a continuous sample path. Is that clear? Any questions?
Positive means positive everywhere.
Yeah,
Fx is positive.
there are two different types of positive. Here, positive definite roughly means that, and you also assume that the kernels are positive because you don't want to be in trouble with the notion of convergence for this series. So if everything is positive, you have a.
It's really non-negative, right?
Yes, it's really non-negative. So, but we will see that. Well, I give you, for instance, for the GFF, I show you how to handle the case when the kernels are not positive. But in the beginning, I just want to treat the case when the kernels are positive. And this is not important for the construction of measures. But Kahn wanted to have a strong, well, a theory where he can show uniqueness. So for showing, in order to show uniqueness, he needs the assumption of positivity of the kernels. So, but we'll see how to handle the situation when you are not positive. Okay. Well, yes. So the kernels are really non-negative. Well, if I want to be coherent, to stick to my notation, I should maybe call them yn. Okay, sorry, I just changed my notation. My sequence of kernels will be called yn. It's better for the following. Okay, so now, in some sense, you have an approximation of K with this series, and well, in some sense, if you set xn is equal to the sum for, well, if you take the partial sums in this series, You should have an approximation of the limiting distribution x, so at least in law. So the Xn, this is some kind of approximation of x. Okay. So if you want to define your measure, it's natural to consider the approximated measure. Well, call it Mn is equal to the sum of to the exponential of xn sigma dx. Okay. So this is an approximation of what turns out to be bad, but it's an approximation of this measure we want to construct. Okay, so what you want to do now is to take the limit as n goes to infinity in this measure and see if you converge towards something, right? Okay, but the thing is that this measure diverges. I won't show you why, but actually, if you just look at for instance, at the expectation of this measure. So if you take a set, a Borelian set A, if you take the expectation of Mn of A, okay, just a simple computation, you have to compute the expectation of the integral over A of this quantity here. Here you can use the Tonelli theorem. You invert integration and expectation. Okay, and here you have just the Laplace transform of a Gaussian random variable to compute. Okay, so you will have 1/2 of the expectation of xn square. Okay, and well, in most situations, the kernel you have here, the big K. So this quantity here, this is the expectation of xn square. If you compute this quantity, it's just the partial sum in the expansion of K. Okay. So and usually K will have a singularity. Okay. If you take x equal y. In most cases, you will have a singularity. I mean that this quantity will diverge. Okay, so this is not a good approach to define your approximated measure like this. Okay, so you have to tame a bit the divergence, so that what is not a bad idea is to divide your measure by the quantity here, which diverges too. Okay, so. The good definition for the approximating measure is rather the following. So maybe I should first detail a bit. Recall that a simple observation. The expectation of xn square, because your processes yn are independent, this is just the sum for k equal 1 to n of the kn of xx. Okay, and it should go as n goes to infinity towards k of xx. This is what I said. Okay, and this quantity for x equal to y is infinity in most applications. Okay, so the quantity you have here should diverge. Okay, so this is not the good definition for your measure. So what is not a bad idea is to divide by the divergence. Okay, so the true definition is rather the following. For the approximating measure, we will take mn gx is equal to the exponential of xn minus the diverging term okay. And now if you take any so remark, if you take any compact set A and you compute the expectation of Mn of A, you get, you do the same computation as here and you get sigma of A. Okay? So now the expectation has a good normalization. Okay? Well, at least you are in a not so bad situation to expect convergence. Okay? So now the other point is that Mn of A for any compact set A, this is a martingale. Okay. And this is the very important point in my definition of kernel of sigma positive type. Because here, when you pass from n to n plus 1, you just add in the exponential the term n plus 1 in the series. Okay, and so you just add yn plus n in the exponential, and it is independent of xn. Okay, so here you have a positive martingale. Well, maybe we can just do this straightforward computation. This is because this is the very important point in Kahn's approach. I just insist on this point. So if you take the expectation, so take Fn equal to the sigma algebra generated by the yk k less than n. So this is the sigma algebra generated by these random variables. And if you just compute the expectation of mn plus 1 of A given Fn, okay. So mn plus 1 is just so by independence of xn and yn plus 1, you have so here you have the expectation of yn plus 1. Okay, and given Fn. So this is a multi-line writing. So so this part is Fn measurable. The xn here is Fn measurable, and the yn plus 1 is independent. Okay, so it's so you get this quantity here by independence, and the fact that the expectation of the exponential of yn plus 1 cancel with the term written here. So here you just get xn of x. So this is just mn. So, as I said, for each, say, compact set A, Mn of A is a positive martingale. So, it converges almost surely towards a limit. And in conclusion, you have the following. For each compact set, you have the convergence, the almost sure convergence of almost sure towards some random variable that I call m of a. So if you just look at this claim, so you have a collection of random variables, but this does not mean that m of a is a random measure, okay? But if you just use the separability of the space of continuous function, it's not hard to see that this implies that the measure mn dx almost surely converges toward a random measure mgx, random measure. So the convergence here has to be understood in the sense of weak convergence of measure. Okay. So weak convergence. Okay, you just take a dense set in the space of continuous function, and you use a countable Tikhonov theorem. Okay, so and this measure is well, by measure I mean positive measure. Okay, so basically, if you have a kernel of sigma positive type, the convergence of this approximating measure is rather straightforward by the martingale theorem. The point is that you don't know what is the nature of the limit, right? Because if you want to have something non-trivial at the limit, you have to ensure some uniform integrability property for your martingales, okay? And this is not clear, okay? So, well, the thing is that this is the first issue. First, you have to show that this limiting measure, well, is it trivial or not? Is it equal to 0? It's possible that the limit is 0. Or can we have some situations where the limit is not trivial? And the second point is that if you look at this decomposition up there are plenty of ways to decompose your kernel K as a sum of kernels Kn. Okay, for instance, just change the order in the expansion. You get another decomposition, or gather some terms to create new kernels, or even take a quite different decomposition. Okay, you want to know if the random measure you've got here is the same in law for all the kernel for all the decomposition you may have. Okay, so this is something I want to explain maybe. So so there are a lot of issues now. This is, well, we have a very simple criterion for convergence ensured by the martingale theorem. Now we have the issue of determining whether the limit is trivial or not, and the issue of determining if the limit is unique in law or not. Okay? So what I'm going to discuss now is the uniqueness in law. Mm-hmm. Okay. maybe I should summarize the issues we have. Two issues now. Non-triviality of M. And the uniqueness of M. I mean, in law.
Could you explain what you mean by uniqueness in law here?
Yeah, okay. I mean that if you take two decomposition like this, you have two procedure here. Take two limiting procedure, and you will have two random measure, m and say m prime. And what I want to show is that this limiting measure have the same law. Okay. In the space of random measure on G. Okay. So the Kahn's theorem is the following. Well, the law of the limiting measure M does not depend on the way on the sigma decomposition of K. Of course, you take two decomposition of the same kernel, because if you take two different kernels K and K prime, you won't have the same law. Okay, but if you take two decomposition of the same kernel, you will have the same law for the measure M. Okay, so this is some kind of I mean, just a universality result. Universality meaning within this. If you want to have a well-defined theory, you cannot be at ease with the fact that your limiting law depends on the decomposition you choose. Okay, so this is the first important theorem given by Kahn, and well, I just want to make a sketch of proof because you'll see how you can use the comparison lemma I just gave you in the beginning. Okay, this is a good example of use. So sketch of proof. So we take we consider two decompositions of K. Say with a prime. Sorry. We take two decomposition of K of this type. Okay, with associated Gaussian processes, I call them YP, sorry, and YP prime. Okay, is it clear concerning the notations? Okay. So I have two decompositions of this type, and or maybe I should keep this blackboard because I have the definition of sigma positivity. So well, So if you take, so you fix P. Okay, so we fix a P and, well, because this sum, because the kernels are positive, this sum increases towards k, right? So it's not that hard to see that if you take a compact set, take a compact set, and epsilon positive, you can find for p prime large enough, you will have the following relation. You will have the sum for k equal 1 to, say, p, we said p, kp of xy, where you take xy in A. You will have the following relation for all p prime large enough. Okay, this is, well, this is because you have increasing sequences, and you can use, well, in France we say the Gini theorem, okay, but you call this theorem, well, this is about the connection between increasing convergence and uniform convergence, okay. Well, you can establish a relation like this. And so now you see that it looks like a relation of comparison between covariance kernels. Okay, here this is the covariance kernel of x of p. Okay, which is the sum for k equal 1 to p of the yk. So this is exactly the covariance kernel of this process, okay? Because the y are independent, the y's are independent, okay? So now here you have the covariance kernel of x prime p is equal to the sum k ranging from 1 to p prime of the y prime k. Okay, but here you have this additional epsilon here that you have to handle. Okay, so what you do is the following: you say that this quantity here is the covariance kernel of square root of epsilon z, where z is just a standard Gaussian law, independent of everything. Okay, is that clear? So z is independent of everything. I mean, all the y's and the y's prime and so on. So this is exactly a comparison between two covariance kernels. First of this process and second of this process here. Okay, so you can use Kahn's inequality, comparison principle, sorry. So, and So now if you use Kahn's lemma, it tells you that if you take for any convex function f, you will have the following. You will have the expectation of the right hand side. So I mean the integral over a of exponential xp minus the variance. I forgot the f. Okay. This quantity is less than the expectation of f applied to the integral over a of exponential of square root of epsilon z plus x prime p prime minus the variance of this process. Okay, so I have epsilon over 2 times the variance of z, which is 1, okay, minus 1/2 minus 1/2 of the variance of x prime p prime. Okay, and you integrate with respect to sigma. So actually, Kahn's lemma was about discrete random vectors, but you can use you can apply the same lemma for the continuum, because you have continuous Gaussian processes here. So there is no harm in taking a continuous version of Kahn's comparison principle. So now here you see that this is valid for all the p prime large enough you consider, and for arbitrary epsilon. Okay. So now if you take so let me write this quantity like this. I have a exponential of square root of z of epsilon minus epsilon over 2, and here I have the measure m prime p prime of a. Okay. So if you take your convex function, well, the thing is that you want to take your convex function bounded. Okay, but this is not a good idea. Okay, because if you take it, well, actually, well, you can. Okay, you can take it bounded. For instance, you have all the exponential function exponential minus something over r plus. Okay, recall that your function f is defined over r plus, taking value in r. Okay, so if you take a convex bounded function over R, this is not a good idea, because there are not so many convex functions which are bounded over R. But here you are over R plus, okay? And so you can take it bounded because you have you have enough functions here, you have all the exponential minus something, okay? So the thing here is that you can take f bounded here, and you know that this quantity here, when p prime goes to infinity, converges towards m prime. Okay, so you can use the dominated convergence theorem. And furthermore, when p prime grows, Kahn's comparison principle tells you that this quantity grows. Okay, because you increase the covariance kernel. Okay, so this quantity is less because this quantity is increasing. It's less than the expectation of f minus epsilon over 2 m prime, the limiting measure of a. Okay, so this quantity does not depend anymore on p prime. Okay, so now you have a relation which is valid for all p. Okay, for all p, this quantity here is less than this one, and you can also apply the dominated convergence theorem in the left-hand side to deduce that because this bound here is uniform in P, you deduce that the expectation of M of A, taking the limit as P goes to infinity, you deduce that this quantity here is less than this one, okay? So this is valid for all bounded convex function F. And so now you just have to get rid of this epsilon here, okay? But as your function, your convex function is continuous, you can also take the limit as epsilon goes to 0, okay? And apply the dominated convergence theorem to say to deduce that we have the following relation, which is valid for all bounded convex function F. Is less than expectation of f of m prime of A. Okay. And so now if you take f equals, for instance, to exponential minus lambda x, you get that. So of course you can replace this sign here by equal, because you do the same job the reverse way, okay, and you get an equality here. So you do the same job as we did here, but the reverse way, okay. So you get the reversed inequality and you get an equality in the end, okay. So now you take f an exponential of minus lambda x with lambda positive, and this tells you that m of A has the same law as m prime of A, okay. Okay, so well, this is a sketch of proof of Kahn's result, okay. Well, actually, because I cheated a bit, because I just showed you here that this random variable has the same law as this one, okay? And this is not a statement about the law of measures. This is just a statement about the law of random variables, okay? So you have to just adapt a bit the proof here. Actually, instead of a set, you have to take a continuous function with compact support on G, because this characterizes the law of the measure, not only the law of the measure applied to a set. Okay, so this is just a bit a small modification of this proof, and you get uniqueness in law for measures.
You can also ask the question whether you have uniqueness of the law of the joint law of the field and the
yes, this is something I want to discuss in the third section of my lecture. But of course you're right, because here, what an important. Well, so I guess it's time to something important is the joint law of the field and the measure, and you can also get something like this, but it's a bit more elaborated. Okay? This is just the simple framework. Okay. Thank you.